Please excuse my sick sounding voice, but hello, I'm Kalina, my partner's name is Evan, and today we'll be presenting about CellCept. So CellCept itself is a drug that actually helps you mitigate rejection. No, not rejection in your relationships or in your graduate applications, but organ transplant rejection. So basically, CellCept is most notably used in order to help patients to weaken their immune system after an organ transplant for a higher chance of the body accepting that foreign organ. As shown in these simplified drawings that you see here, patients often struggle post-transplant to accept a new organ as the body recognizes a foreign object as a threat to the health of the body. So without the use of medication, the body will try to reject the newly transplanted organ, and that is where CellCept comes in. So simply put, CellCept will weaken the body's immune system, which allows it to more easily accept the new organ. So in our presentation, we're going to take you on our academic journey in order to learn more about CellCept, the drug. So what is it, how is it made, and the chemistry behind the prodrug CellCept. So some background information about CellCept before we get into the chemistry and the reactions. What exactly is CellCept? So CellCept is just the manufactured drug's name. The actual structure is called mycophenolate mofetil, which is MMF for short. So given that the drug's purpose is to weaken the immune system, the drug itself has to be prescribed by a medical professional. So it's often taken orally as a pill, which is seen in the slide's images, but MMF itself is a prodrug, which we learned means that it enters the body in an inactive form, but later becomes activated through some type of metabolism. So for CellCept, this metabolism happens inside the liver. So MMF is metabolized into mycophenolic acid, which is MPA for short, which is the active form of the prodrug MMF. So this active form is what actually weakens the immune system. Initially, MPA was directly used to treat patients, but we later found out that MPA has gastrointestinal and carcinogenic side effects, so this pathway was discontinued. So this once again emphasizes the importance of MMF being a prodrug because allowing the active form to only affect the target once it's inside and activated and metabolized in the liver, rather than affecting other parts of the body if it were inserted just as MPA and not as a prodrug. So as stated, the purpose of CellCept is to primarily treat organ rejection from organ transplants, specifically in the heart, liver, and the kidney. It is also sometimes used to treat autoimmune diseases as well. So the retrosynthesis of CellCept follows the metabolic process we talked about in the previous slide. So transformation from the prodrug MMF into the active form MPA. So as shown in this diagram, MMF would be formed from the ethanol structure on the top and the mycophenol chloride shown on the bottom. So this reaction would occur in ethyl acetate for 2 hours. So the next step would then be to form the MPA from the mycophenol chloride. So we would do this by combining the mycophenolic acid and the diethylamine in ethyl acetate for 30 minutes, followed by combining it with SOCl2 in ethyl acetate for 2 hours. This slide shows the overall mechanism scheme for the first step, which is the conversion of MPA into acid chloride structure with the use of SOCl2. The lone pairs on the oxygen in the hydroxyl group are going to be used to form a new carbon-oxygen double bond, which forces the carbonyl carbon's electrons in the carbon-oxygen double bond to attack the sulfur in the SOCl2. So then the electrons from the sulfur-oxygen double bond are going to be pushed up onto the oxygen. The electrons on this negatively charged oxygen are going to kick back down, which then kicks chloride off as a leaving group as it forms that sulfur-oxygen double bond. Then the chlorine that is a leaving group is going to come back and attack as a nucleophile, attack the carbonyl carbon, which then kicks up the electrons from the carbonyl bond onto the positively charged oxygen. Finally, the electrons are going to move intramolecularly in order to form HCl, SO2, and the final carbonyl group. So here is the overall mechanism for the second step of the synthesis, which is the reaction between the acid chloride and the ethanol structure in order to form CellCept. So first, the hydroxyl group on the ethanol structure acts as a nucleophile to attack the carbonyl carbon of the acid chloride. This then pushes the electrons in the carbonyl double bond up onto the carbonyl oxygen. In this step, we see those electrons on the negatively charged oxygen go back down to form that carbonyl double bond between the carbon and the oxygen, kicking off chlorine as the leaving group. Finally, we have that chlorine that left as the leaving group come back in to grab that hydrogen on the positively charged oxygen. The electrons between the oxygen-hydrogen bond go back to the oxygen to form CellCept. Finally, we have that chlorine.
Hi everyone, my name is Evan, and I'm really excited to be talking to you today about the biosynthesis of MPA, the active form of our prodrug CellCept. So MPA was actually discovered in 1893 from Penicillium brevicompactum, and it was the first natural product antibiotic to be isolated and crystallized. Here on the slide, you can see the full biosynthetic pathway, which wasn't really elucidated until really recently, 2019. And the full biosynthesis takes 7 enzymes, and the major pathway involves 11 steps to the final product. Here in the diagram, you can see that the bold arrows represent major pathways, the minor pathways are in solid arrows, and the shunt pathways are in dashed arrows. For brevity, I'm just going to be talking to you today about the major pathways. The biosynthesis starts when the enzyme MPAC converts 1-acetyl coenzyme A, 3-malonyl-CoA, and 1S-adenosyl L-methionine to 5-methyl orsolinic acid. Then the enzyme MPADE hydroxylates that, and there's an intramolecular lactonization to form this bicycle. Once the bicycle is formed, MPAA uses 1-farnesyl pyrophosphate and farnesylates the compound, which is adding that long branch fatty acid chain. Then MPAB converts it to what's called mycophenolic aldehyde, and through an oxidation, it becomes a carboxylic acid. Then the enzyme MPAG methylates it, and the protein PBACL891 converts it to an acyl coenzyme A. This moiety at the end of the molecule is important for the next step, which is peroxisomal beta oxidation. And you can see in this slide that each oxidation removes a 2 or 3 carbon unit before getting to the final product. So with one beta oxidation, you lose 2 carbons, and then the second beta oxidation, you lose 3. And then finally, the enzyme MPAH releases coenzyme A from the molecule and gives you your final product, mycophenolic acid. The last thing we wanted to say about CellCept is that while it is useful for preventing an immune response following organ transplants, there are some potentially harmful side effects. There's an increased risk of certain cancers when taking CellCept, including lymphoma and certain skin cancers. There's also a risk of miscarriage in the first trimester, and if the pregnancy does come to completion, there's an increased risk of birth defects in the child as well. And finally, there's an increased risk of serious, potentially life-threatening infections due to the fact that CellCept does weaken your immune response.